Hello, everyone. It's my great honor to speak at OpenXdata, and I'm Hanfei, Technical Director of JD Real-Time Data Platform. And today, I'd like to share our latest architecture evolution of Apache Hudi at JD.com. In today's session, I'll cover four key parts. First, JD's enterprise data lake architecture and our latest in-house Hudi features, and real-world business practices, and our future technical roadmap. JD has built a mutual enterprise-grade data lake architecture based on Apache Hudi, and beyond Hudi's native capabilities, including, for example, ACID transactions and incremental data pipelines, we've deeply optimized the framework to fit our unique business needs and developed a series of in-house features. To give you some examples here, binary copy enables fast and large-scale data migration, and partition-level bucket index brings flexibility to the number of bucket setting. And we also support partial column updates for multi-time step scenarios. And on top of these features, we built a native I/O, hybrid storage, and our customized LSM tree-based MR table format. All of this tailored optimization allow Hudi to perfectly adapt to JD's high concurrency and massive scale business scenarios. Let's start with our overall ecosystem coverage. And first, for data ingestion, we support mainstream sources, including MySQL, Kafka, Flux, and Hive, and as well as Hudi itself. And this enables seamless data ingestion across relational databases, message queues, and data warehouses. For compute and query engines, we fully support streaming with Flink, and batch processing with Spark and Hive, and ad hoc analytics with Doris and Presto. This full-stack engine coverage meets diverse analytical requirements across all of our business teams. At the storage layer, we primarily rely on HDFS from Hadoop system, paired with our self-developed distributed file system, TrueBell-FS. Together, they delivered stable, reliable, and cost-effective storage for our entire data lake system. To date, our Hudi-based data lake has reached nearly 400 petabytes physical storage, and with over 5,000 production tables running stably. Next, let's dive deeper into our core in-house Hudi optimizations. First up, our LSM tree-based MR table format. This is one of our largest and most impactful features. And the native MR table came with three major challenges in our high-scale production environment: and performance bottlenecks, stability risks, and concurrency limitations. Before I walk through the challenges, and a quick clarification, all our custom features are built on top of Apache Hudi community version 0.13.1. So all pain points I'll mention here are specific to this baseline version. Back to the challenges, and on performance, under high throughput write workloads, native MR write and update throughput could not meet our production SLA. And when using bucket indexes with large bucket counts, log file writing triggered expensive list operations. Additionally, row-based arrow storage forced full row reads for partial column queries, which results in poor I/O efficiency and slow query. Stability, the original compaction process loaded all updated data into memory at once, which frequently caused out-of-memory errors. And meanwhile, streaming compaction competed for resources with Flink streaming jobs, and leading to recurring task failures. So to alleviate this, teams had to deploy independent compaction tasks manually, often a dedicated Spark job, which greatly increased development and operational overhead. On concurrency, a native MR table lacked robust concurrent update support. Whenever we run data backfills or a data repair, real-time streaming job had to be paused. Moreover, multiple jobs writing to the same table could only run sequentially, which significantly increased the end-to-end data latency. So to solve these pain points, we designed and implemented a custom LSM tree structure for Hudi. This core in-house capability follows clear and production-oriented design principles. And first, let's talk about file group organizations. Our LSM tree solution is fully built on the bucket index with a two-layer file group structure. The LO layer stores all incremental updated data. Data here is continuously sorted and merged via minor compaction. The L1 layer consists of fully compacted and stable data files generated either through full compaction or during table initialization. This layer design ensures low write latency and efficient compaction and faster queries. We also made two critical upgrades to data transfer and storage. At first, we adopted native compute engine data formats to eliminate redundant data conversion overhead. And second, we replaced the original error log format with Parquet. We know Parquet enables native sorting and deduplication while supporting column pruning and predicate pushdown, which delivers massive query efficiency gains. Now let's take a look at the optimized LSM tree architecture for Flink streaming rights, which powers our low latency and high concurrency real-time data ingestion. As you can see on the slide, here's how the pipeline works. Upstream data flows into Flink in native raw data format. After repartitioning, data enters the disruptor ring buffer in each subtask, then flows into corresponding bucket sort buffers for in-memory sorting and deduplication. Finally, sorted data is written to Parquet files and persisted to the storage. We optimized nearly every key stage of this pipeline, which maybe can be summarized into five major improvements. First, zero data format convention. The entire pipeline uses Flink's native raw data directly with no extra serialization and deserialization, maximizing transmission efficiency. And second, we call balanced partition assignment. The original hash partitioning led to severe workload skew. In production, we found some subtasks proceed far more buckets while others stayed idle. To fix this, we built a global view we call remote partitioner that achieves even workload distribution across all subtasks. And the third one, we call decoupled data production and consumption. We leveraged the disruptor ring buffer to implement async processing, separating data reception from downstream write logic. This design improves throughput significantly, even during data backlogs. And also optimize the memory management. We unified the memory allocation via memory segment pool, which effectively reduce JVM GC pressure and stabilize long-running streaming jobs. And the last one, lightweight in-memory sorting. We introduced the binary in-memory sort buffer, which stores data in binary format to cut memory usage. It performs a pointer-based sorting and removes unnecessary object copy overhead entirely. Reading LSM tree data is also an important aspect. We use sort merge reader to complete multi-way merge sorting, merging records with the same primary key from multiple data stream efficiently. And there are two common multi-way merge algorithms, min heap and loser tree. The key difference is that the number of the comparison operations during tree adjustment. Uh, when merging a large number of file paths, the loser tree requires only half of the comparisons of a min heap and offering much better performance. And let me briefly explain the mechanism as shown on the right. Green nodes represent leaf nodes, which fetch records from data files and compare values with their parent blue nodes. The smaller record moves upward while the larger one is marked as a loser and retained in the parent node. This iteration continues until the top red node outputs the smallest global record. However, Hudi ML scenarios introduce extra challenges. A single data file may contain multiple records with the same primary key, which requires additional merging while merge function. The original loser tree implementation reuses Hudi record objects, causing data conflicts. So to avoid the conflicts, we have to perform deep copies for all output records, which brings huge performance overhead. So to solve this bottleneck, we then designed we call a state machine-based loser tree. We added custom states for all tree nodes and triggered state transitions during each comparison. We also record the leaf nodes indexes corresponding to duplicate primary keys. So with node state management and index tracking, we can quickly locate all records with identical primary keys in one pass. And this avoids repeated tree adjustments and redundant comparisons and completely removes expensive deep copy operations. And overall, this optimization brings a 15% read performance improvement. We ran benchmark tests using TBCDS and Nextmark datasets to compare our customized MR LSM tree solution with the original Avro-based MLR implementation. And all test environments are identical with job execution time and data processing latency as core metrics. The results speak for themselves, and our LSM tree implementation delivers 2 to 4x better write performance and 4 to 6x faster reads than the native arrow-based ML format. Next, I'd like to talk about our hybrid storage optimization. By default, Hudi's metadata design binds one table to a single file system and a fixed storage path. This means storage clusters load and network bandwidth directly determine job performance. In large-scale real-time ingestion scenarios, this often leads to job stalls and slow file writes and even sometimes checkpoint timeouts. These issues increase data latency and undermine streaming job stability. To address these I/O bottlenecks, we referenced Hudi Community RFC60 and implemented the custom Hudi storage strategy interface. This interface standardizes file storage policies and exposes universal APIs to resolve physical file paths. Built on top of unified Hudi storage abstraction, our Hudi hybrid storage can automatically route file operations to different storage systems. So with this design, one single Hudi table is no longer limited to one storage system. Data can be distributed across multiple clusters, which balances storage load and fundamentally solves single cluster I/O bottlenecks. Let me explain how this works in production. We maintain two types of HDF clusters, and first, we call shared HDF clusters with a large capacity and low cost, but performance fluctuates heavily during offline computing peak hours and often causing job congestion. Second, the high performance HDFS clusters with smaller capacity and higher cost, but extremely stable read and write performance with negligible fluctuate. I think perfectly suited for real-time workloads. Based on their respective strengths, we designed a we call cache layer hybrid storage strategy. All real-time written data first lands on high performance HDFS classes to guarantee stable write throughput. Then async compaction and clustering services merge small files and migrate consolidated data to low-cost shared HDFS clusters. This strategy preserves high-performance cluster resources for critical real-time workloads and reduces the overall storage costs. And during queries, we built a unified cross-storage file view to ensure consistent and accurate query results. Thanks to hybrid storage, the stability of our large-scale real-time ingestion jobs has improved dramatically, and compared with the traditional single storage architecture, our write performance and job stability have nearly doubled. Finally, moving on to our native I/O capability, we developed the Hudi native I/O SDK to enable AI training engines to read the data lake tables directly. The native I/O solution consists of four core models: data invocation layer and cross-language transformation layer, and Hudi view management layer, and high performance query layer. As shown in the slide, here's the core workflow. Users send requests from the data invocation layer, and the request pass through cross-language convention, and the Hudi view management layer fetches qualified file slices with partition pruning enabled. And after parsing and shuffling file splits, we can effectively reduce model overfitting and improve generalization capability. And then core parameters are passed to our REST-based high-performance query layer. We customized data fusion physical planes and developed key operators, including packerator and submerge and union, and powered by the data fusion engine and the arrow memory formats. We support efficient file reading, multi merging, and full capability with our customized Hudi LSM tree format table. A benchmark results show that our data fusion and arrow-based packerating is 2x faster than Spark vectorized packerating and 7.5x faster than the original arrow-based reading. This completely resolve I/O bottlenecks for AI sample engines. Now let's move to the third part of business practices. Uh, we upgraded our traffic data warehouse to a Hudi data lake architecture where we faced three tough technical challenges. And the first one, extreme partition data skew in traffic scenarios, and with a maximum skew ratio of up to 1 million times. And second, massive data scale. Our daily incremental uh, exposure logs reached the 100 billion level, while click and browse logs hit 10 billion per day, which putting extremely high demands on read and write performance throughput and compaction efficiency. And third is the original arrow-based MR tables did not support concurrent updates, just as we mentioned before. So any offline backfill or field repair would block real-time write streams. With our customized 2D capabilities, we successfully completed the architecture upgrade for the traffic common layer. We unified separate real-time and offline pipelines into one single data lake architecture, stably supporting 100 billion level daily updates with high throughput and low latency. Leveraging Hudi partial column updates, one single Flink job can consume multiple Kafka topics simultaneously and write streaming data to Hudi tables in real time. And combined with our asymmetry story format, overall read and write performance improved by over 2x. And besides periodic Spark job support concurrent data repair and backfill, and to fix extreme partitions skew and unbalanced bucket allocation, we built a partition level customized bucket strategy. And we also developed a timeline service-based remote partitioner and completely eliminating subtask level bucket skew and improving cluster resource utilization at the same time. Underlying hybrid storage further guarantees stable ingestion throughput and enabling reliable near real-time processing for 100 billion scale traffic data. Finally, let's walk through our future Hudi roadmap. We'll continue to invest heavily in the research and development of Apache Hudi. And in fact, we have already made some progress in the following directions. At first, we plan to upgrade our internal JD Hudi version to Community Edition 1.1.x or higher. And second, we'll iterate on native I/O and achieve full seamless integration with Spark and Flink engines. And we'll expand Hudi's CDC functionality, including decoupling CDC data generation from a compaction service and enabling we call the input CDC mode. And also we'll integrate the lens format into our system to support multimodal data scenarios. And last one, we'll continue exploring the Flux plus Hudi combined architecture to build a unified lake stream system. And okay, that's all for today, and thank you all for listening. Thank you.